Alright guys, so today we're going to continue. Yesterday we started with polar versus non. Everybody please up here. Thank you so much. Yesterday we started off with polar versus non-polar covalent bonds, but yesterday was a hot mess of a day, so we're just going to recap. In your notes, you should have already written down something about non-polar being electron pairs that are equally shared. So for a non-polar bond, these electrons are equally shared between the atoms in the bond. First and foremost, when I'm talking about polar and non-polar, I'm talking specifically about covalent bonds. Covalent means that, is it like a metal and a non-metal, two non-metals? What's covalent? Non-metal and a non-metal. Remember, ionic was metal and non-metal. Covalent is two non-metals. Look up here. All right, so here's hydrogen and hydrogen. Those are clearly two nonmetals. And when these guys have electronegativities that are approximately the same, then the electrons are being shared equally. What is electronegativity? What does that mean? Yes. Yeah, so it's the ability to hold on to electrons. I don't want to have to move you guys. So because both of these they're the exact same atom, they're going to have the exact same electronegativity. Is any one of those going to pull the electrons closer than the other? No, they're the exact same atom. So therefore, these are being equally shared, and we call that a non-polar bond. However, down here, I have chlorine and I have hydrogen. While chlorine is clearly closer to fluorine, we know that fluorine is the most electronegative atom. Chlorine is closer. So chlorine is going to pull the electrons towards it because it's more electronegative. Hydrogen's all the way over here, very far from fluorine. It's not that electronegative, so hydrogen is weak. It cannot hold the electrons, and so it kind of gets pulled towards the chlorine. That's why this is very electron dense over here, and then this doesn't really have a lot of electron density. Because the chlorine has the electrons closer to it, it gets what we call a partial charge. Everybody should have this symbol in their notes, this delta symbol. So this delta symbol means partial. That little S funny looking thing, that means partial. And because the chlorine has the electrons close to it, it's partial negative. So the more electronegative atom becomes partially negative. Whereas the other guy is partially positive. Why don't I have complete charges? Why are they partial and not complete, like in an ionic compound? Well, in an ionic compound, I'm completely losing electrons and completely gaining. So I have complete charges. These aren't really losing and gaining, they're just like closer or further away. Yes? This delta means partial. So this is partial negative. And then we have what we call an induction arrow. So this arrow, it kind of looks like this, and it has a little line through the tail. That's what we call an induction arrow. The arrow tells us which way the electrons are going. Clearly, the electrons are always going to go towards the electronegative one. So the arrow's pointing towards the chlorine. That means that chlorine is going to be partial negative and the hydrogen is partial positive. Now, another thing, I can't even talk. Where the word polar came from, excuse me. Polar comes from like opposite ends of something. So just like we have the North Pole and the South Pole, opposite ends of the globe, we have opposite charges. And that's where the word polar came from, opposite poles of a compound. This slide I don't really care too much for. If you wanted to read it, it's basically reiterating everything we just talked about. This periodic table, we already talked about this yesterday. This is a different type of periodic table. It's not the normal one. It's electronegativity. So the number at the bottom is not the mass like we're used to seeing. It's the electronegativity of each element. It can range from 0 all the way over to fluorine, which is approximately 4.
Is it always going to be fluorine?
Fluorine is the most electronegative. It will always be that, yes. All right, so the difference in electronegativity dictates polarity. This is all kind of review from yesterday. We know that if you have two atoms that are exactly the same, that's kind of what this is showing. This could have been like the hydrogen and the hydrogen from that first example. We know it's always going to be what we call pure or non-polar covalent. So pure covalent, non-polar covalent, they mean the same thing. So anytime you have two atoms of the same elements that are bonded together, it's always nonpolar. Neither one of them is more electronegative than the other. And that range is from 0 to 0.4. Polar covalent is when you have two different atoms. One is more electronegative When you subtract their electronegativities, it falls in between this range. And then ionic is when it's greater. This one says 2. The other one on the next slide says 1.8. Just remember, guys, every single source that you get is going to have different experimental data. So 1.8 to about the same thing. In this class, I'll reference 1.8. So anything greater than 1.8, we're going to consider ionic. And again, you can see this is completely transferred electrons, and we have opposite charge. This is the same chart. You guys should have this chart in your notes. This is the one that I will be referencing. Everybody got this in the notes? Awesome. So that was a recap of yesterday. This is some examples. I think, did we get a chance to do HCl in this class? All right, we're going to do it today. So first thing we need to do is draw the Lewis structure for HCl. I already have it on the board, so I'm going to go through this quick, and then I'll let you do the other two. So for HCl, hydrogen has 1 valence electron. Chlorine, 1, 2, 3, 4, 5, 6, 7. He has 1 little dot all by himself. Alfred, how many bonds can he make? 1. Chlorine has 1 dot. How many bonds? 1. Let's go ahead and bond them together, forming HCl. Easy, right? Okay. That's the Lewis structure. That's the first step. The next thing that we need to do is figure out whether this bond is polar or nonpolar. So we're going to have to get the electronegativities of both of these elements. So I'm going to go back to the periodic table in the notes, and I'm going to look for fluorine. There it is, 3.16. I also needed hydrogen. Hydrogen is 2.20. So 3.16 minus 2.20. If I did the math, I'd get 0.96. This number is the difference in electronegativity. So I'm going to find this number on the chart. So is 0.96 less than or greater than 0.4? Greater. So clearly this is not pure covalent. In order to be pure, it has to be less than. It is polar. Is it greater than 1.8? No. So clearly it's not ionic. Also, it's not a metal and a non-metal, so it's obviously not ionic. It falls in between those two numbers, so it's called polar covalent. So this bond is a polar covalent bond. Good? Everybody got this in the notes? Can I erase it? All right. The next one is super easy. What did we say if it's two elements that are exactly the same bonded together? It's always going to be what? Pure covalent. So iodine and iodine. Let's show the Lewis structure real quick. So 2 iodines. Iodine has 7 electrons because it's in group 7. 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How many bonds can iodine make? 1. It has 1 dot by itself. Same thing here. That's going to create a bond. The product is going to look like this. The molecule is going to look like this. Good? All right. I want to figure out whether this is polar or non-polar. If I were to do the math, I go to my periodic table with the electronegativities. Iodine is 2.66. So iodine bonded to iodine, so 2.66 minus 2.66, that equals 0, right? Is anybody confused? All right, very good. So you come back to this chart. It's even easier to see here. 0 is nonpolar. Very good, nonpolar. So number 2 is easy. Number 3 is going to get tricky. And that's actually the main part of today's lesson. So go ahead and get the paper out, the one that we did at the beginning at the front of class. All right. So up until this point, we've been doing our Lewis structures pretty basic. Like you just draw the valence electrons and you pair up the ones that are alone, right? That's kind of like the training wheels of Lewis structures. It works, but it doesn't work all the time. There are some more complicated Lewis structures that are going to require more steps. So this paper is going to give you all of the steps to make the perfect Lewis structure every time. I hope you guys feel good with the Lewis structures we've been doing, because now it's going to get even more complicated, or at least more detailed. So we're going to work out NO2 negative, the third example, on this worksheet. I'm going to close the screen so that I can use the... Let's do number 3. All right, NO2 minus. Number 3 is a little bit more difficult of an example. So in class today on 12/12, I gave you guys a handout that looks like this. So it says steps to making a perfect Lewis structure. We're actually going to start using these steps every time. The reason is, in the previous examples, it was really easy. I said put the valence electrons, mash up any ones that don't have partners, and we'll get the Lewis structure. It's not always going to be that easy. So this way, even though it's a longer, more complicated method, will work every time. So this was kind of like training wheels, just to kind of get you familiar with what Lewis structures are. And now we're going to start doing this system from this point forward. It's going to work every time. So the first step in this system, and I'm going to do the Lewis structure here, is to count the total number of valence electrons in the compound. Again, the compound was NO2 minus. So I have 1 nitrogen. I know I have 1 because there's no number here. If there is no number here, that means I just have 1 nitrogen. And I have 2 oxygens. This subscript 2 means I have 2 oxygens. In order for me to figure out the total number of valence electrons, I came to this is just a regular periodic table, not the electronegativity one. So there's nitrogen. Nitrogen is in group 1, 2, 3, 4, 5. I know it says group 15, but remember in my class I use the AB system, so I just count the tall groups. So group 1A, 2A, 3A, 3A, 4A, and 5A. So nitrogen is in group 5A, therefore it has 5 valence electrons. Oxygen is in group 6A, and it has 6 valence electrons. All right, I'm going to add up all of those valence electrons to get the total, which is 17. But then I need to take into account this negative charge. Well, a negative charge means that you gained an electron, which means I need to add 1 electron. And I have 18 total electrons in this compound. All right, step 2. Create a carbon skeleton, create a skeleton by placing the least electronegative atom in the center and all other atoms around it. Well, in between nitrogen and oxygen, nitrogen is the least electronegative. Let's go to a periodic table to find out why. On the periodic table, we know that fluorine is the most electronegative atom. So the closer to fluorine, the more electronegative. Oxygen is closer, so oxygen is more electronegative. Therefore, I put nitrogen in the center because nitrogen is less electronegative. So there we go, I've put nitrogen in the center. Then it says to use single bonds to connect the atoms together. A single bond is just a single line. And lastly, once this is done, subtract the number of electrons it took to connect these atoms. Remember that there are 2 electrons per single bond. Well, I had 18 electrons to start off with. There are 2 here and 2 here, so I used 4 electrons. And I now have 14 electrons remaining. Step 3. Begin using electrons to fill the octet of the peripheral atoms. Peripheral means outside. So I'm going to redraw. And now I'm going to start adding up. Oxygen has 2. This bond represents 2. So I need to add 6 to get to 8. 1, 2, 3, 4, 5, 6. Same thing. 2, 3, 4, 5, 6, 7, 8. All right, so now this oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. I filled up their octets. I used up 12 electrons. 2, 4, 6, 8, 10, 12. So I'm going to subtract 14 from what I had to begin with from this last step, minus 12. I now have 2 electrons left. So I'm going to come down to step 4. If you have any remaining electrons to work with, place them around the center atom. Sometimes you're not going to have any left. Sometimes after this step, you'll end up with 0, so you'll just skip step 4. But I do have some left, so I'm going to do step 4. I'm just redrawing the guy from the previous one. And then these 2 electrons are going to go on the center atom. I got a good question today that said, why don't I put those 2 electrons far away from each other, like one on the top and one on the bottom? Well, when you're doing the Lewis structures in this method, just put them together. There is a reason behind it. It has to do with molecular orbital theory. We'll talk more about that maybe at the end of the year. If not, just trust me. Just put them together when you're doing this method. All right, let's move on to step 5. Step 5 says make sure that all the atoms satisfy the octet rule. This means that all atoms should have 8 valence electrons. There are a few atoms that can break the octet rule. See the exceptions below. So this is a list. This is a list of hypovalent atoms, atoms happier with less than 8 valence electrons. Hypo means less, valent referring to valence electrons. So hydrogen is happy with 2 valence electrons. Helium is happy with 2. Boron, this is a typo, you guys should have corrected it. Boron is happy with 6 valence electrons, not 3 but 6. And beryllium is happy with 4 valence electrons. So those are what we call hypovalent exceptions. They do not need to have 8. They're happy with this number, these amounts. We also have a list of what we call hypervalent atoms. These are atoms that are happier with more than 8 valence electrons. So they might have 8, they must have at least 8, but they could possibly have more depending on the compound. So all elements in row 3 and below on the periodic table can hold more than 8 electrons. So going to a periodic table, these are the rows. So row 1, row 2, row 3, everything in row 3 and below can have more than 8. So we'll have examples of that in the future. For now, I just wanted to give you a little bit of a preview on that. All right, so let's redraw the compound from the previous step. So far, this is what we have. All right, and we have no more electrons, so we're all done. Step 5 said to make sure that they have a complete octet. Well, first and foremost, oxygen, nitrogen, and oxygen, none of these are in my exceptions, so they have to have at least 8. So oxygen has 1, 2, 3, 4, 5, 6, and this counts as 2, so 7, 8. He's happy. Same thing here. It's the exact same guy. This is not a lone pair. Sorry, guys. This should be, there we go. That's what it should be. So 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen, however, only has 1, 2, 3, 4, 5, 6. Remember that covalent compounds share these 2, so these 2 count for both oxygen and nitrogen. So he has 2, 4, 6. He's not happy. What do I do when nitrogen isn't happy but I have no more electrons? Because in the last step, I used up all my electrons. Well, I need to take a lone pair from one of my peripheral atoms. It doesn't make a difference whether I took this lone pair or this lone pair, or this one or this one or this one. It makes no difference. I just needed a lone pair. This is exactly the same as this, so it made no difference. I'm just going to take this one, and I'm going to make what we call a double bond. So I'm putting the arrow from the lone pair to the bond to show that I'm creating a double bond. Here's the result. This guy didn't change, so I'm just redrawing him. But now I don't have a single, I have a double bond. Oxygen has 1, 2, 3, 4 electrons left, so 2 lone pairs. All right, let's see if everyone's happy. 2, 4, 6, 8, oxygen's good. 2, 4, 6, 8, nitrogen's happy now. And this one never changed, so he still has 8. 2, 4, 6, 8. Everybody is happy. So we're done with step 5. Last but not least, step 6. We're going to do the formal charge of all of these atoms involved. So I'm going to redraw it. Nitrogen, with its now double bond to oxygen, and single bond to this oxygen. Formal charge is really easy, guys. I know it seems like a fancy word, but it's not. So we can use this little formula. It's very straightforward, very easy. The formal charge is equal to the number of valence electrons minus the electrons in lone pairs minus the bonds. So we're going to do this for each individual atom. I'm going to get a different color. Okay, let's start off with this oxygen. This oxygen has a valence of 6 because oxygen is in group 6. The group tells me the number of valence electrons, therefore that is the valence. And then I'm going to count the number of valence electrons as 6 minus the number of electrons in lone pairs. Well, I have 1, 2, 3, 4, 5, 6 electrons in lone pairs. minus the number of bonds. Well, oxygen has 1 bond. 6 minus 6 is 0, minus 1 is negative 1. This oxygen has a formal charge of negative 1. We put the formal charge right next to the atom. And this is just the work to show how I got it. Let's do nitrogen next. Nitrogen is in group 5, so it has a valence of 5. Next, I need to count the number of electrons in lone pairs. There are 1, 2 electrons in lone pairs, so minus 2. And then I need to subtract the number of bonds. Each line counts as a bond. So 1, 2, 3 bonds. 5 minus 2 is 3, minus 3 equals 0. So nitrogen has a formal charge of 0. If it's a 0 formal charge, I don't have to put a 0. It's just, I know that there's no formal charge. It's 0. Lastly, let's do this oxygen here. Oxygen, again, has a valence of 6. 6 minus the number of electrons in lone pairs. This oxygen has 1, 2, 3, 4 electrons in lone pairs. Minus the number of bonds. This oxygen has 1, 2 bonds. Minus 2. So again, every line counts as a bond. 6 minus 4 is 2. Minus 2 is 0. So this oxygen has a formal charge of 0. All right. Now that I figured out all the formal charges, let's figure out the net charge on this compound. This is negative 1, this is 0, and this is 0. So again, negative 1, 0, and 0. To find the net charge, you just add those together. So here we have negative 1 plus 0 is just negative 1, plus 0 is still negative 1. This is the net charge. Notice this matches the original charge on the compound, and that's how you know you did it correctly. All right, that's it. That's how we found the Lewis structure with all of the correct charges for NO.